Okay, let's dive deep. Today, we're looking at something huge. The convergence of quantum computing and artificial intelligence. It feels like the next big shift.
Absolutely. You shared some fascinating sources, and they really paint a picture. Quantum isn't just theory anymore. It's becoming practical uh, innovation.
Right. And our mission today is to map out why this quantum layer seems essential for, well, the future of the AI economy.
It's moving fast. For years, quantum felt like something distant, but the sources show real commercial traction now.
There's this central comparison in the material that really caught my eye. Investing in quantum now is like backing cloud infrastructure back in the early 2000s.
Exactly that. Think AWS, but maybe even more impactful. That's the core analogy.
That is a powerful image. Cloud, fundamentally changed everything. But the sources hint quantum's trajectory might be even steeper, faster maybe.
Well, yeah, steeper and faster seem right. The big difference is quantum isn't really waiting for a market to emerge. It's plugging directly into an existing massive demand.
You mean AI's demand for more power?
Precisely. When cloud started, the business case was a bit speculative, right? Mass virtualization. Now, the need for computational acceleration for AI, it's not just proven, it's frankly desperate.
Okay, so that need pulls the adoption curve forward much faster.
Dramatically faster. And the tech itself, it's built for efficiency in a way early cloud wasn't necessary.
So the core concept, let's nail this down. Quantum computing doesn't replace AI. It elevates it, lifts it up.
Elevates is a good word, yeah.
So let's unpack that. Why are our current computers, our classical systems, hitting a wall? They're incredibly powerful, but what can quantum do that they just can't? Why is it this missing link for the next wave of AI?
It really boils down to the fundamental way they handle information. Classical computing relies on the bit, 0 or 1, on or off.
Binary. Yeah.
Right. But AI, especially when tackling really complex stuff like optimizing global supply chains or simulating how drugs interact or predicting chaotic financial markets, it's dealing with massive sets of probabilities, interconnected possibilities, not just simple linear steps.
And classical computers, even though they're fast, they basically have to check possibilities one after the other, right? Brute force it, in a way.
Exactly. They run into what's called a combinatorial explosion. Just too many options to check sequentially. And that's where quantum steps in with the qubit.
The quantum bit.
Yep. Because of quantum effects like superposition, a qubit can be 0, 1, and kind of everything in between, all at the same time.
Okay.
And then, when you link these qubits together, using another effect called entanglement, the computational space just explodes.
Yeah.
Exponentially.
So suddenly, problems with millions of variables don't need millions of sequential checks.
Correct.
Huh.
The system explores the potential solution space concurrently, all at once, in a sense.
That obviously changes the speed equation dramatically. But the sources also kept mentioning energy efficiency and sustainability. How does more computational power actually reduce the energy footprint? That seems counterintuitive.
That's actually one of the most exciting parts. Scaling traditional AI means building these enormous data centers, running constantly, consuming just staggering amounts of power, often for tasks that are, let's be honest, computationally inefficient.
Lots of trial and error.
A huge amount. Quantum computing, because it can handle optimization and simulation with such speed and precision, it radically cuts down on that wasted computation.
Ah, so it finds the best path much, much faster without churning through all the bad paths.
Exactly. Instead of brute forcing billions of slightly wrong answers, quantum algorithms can kind of zero in on the optimal solution almost instantly for certain problems.
Okay, I see.
That's why people are calling it the new energy source for AI. It fuels algorithms that can learn and adapt in real time, but without the massive energy cost we associate with today's supercomputers. It lines up perfectly with, global sustainability goals.
This idea of innovation compounding at quantum speed is really exciting. But, you always wonder about the hype. Let's ground this. What are the tangible benefits showing up now? Real advantages in fields like finance, biotech, materials science.
Yeah, good question. The sources point to 3 main competitive advantages that are already making a commercial difference, not just theory.
Okay, what's number 1?
Efficiency. We touched on the speed, but think about the impact. In finance, quantum-boosted AI could run complex risk assessments, Monte Carlo simulations in seconds instead of hours. For a trading desk, that time difference is...
Oh, yeah.
It's everything.
Game-changing.
It really is. Tackling problems exponentially faster than even the biggest classical supercomputers.
Okay. And the second advantage. This one seems to hit a major global nerve. energy use.
Yes, like we said, traditional AI's energy hunger is becoming a real problem, logistically, regulatorily. Quantum machines, while complex to build, fundamentally use much less energy per calculation for these specific types of hard problems.
So a direct advantage for, say, logistics companies optimizing routes.
Absolutely. Optimization translates directly to lower fuel consumption, lower energy use overall. It's a clear win.
And the third one, accuracy. This feels like where the really groundbreaking discoveries might happen.
That's right. Accuracy, especially in simulating complex systems, because quantum computers operate using quantum mechanics, they're naturally good at modeling things that are also quantum, like molecules, chemical reactions, material properties.
So drug discovery, designing new material.
Exactly. Simulating precisely how a new drug molecule might fold or how chemicals react. Classical computers have to approximate that stuff, often poorly. Quantum systems can model it with incredible precision. That could shave years off R&D.
Wow. Okay, so that combination, the speed, the energy savings, the pinpoint accuracy, that really pushes this beyond theory, which brings us to the companies actually doing this, making money from it.
Right. And we should probably focus on two key players, mainly because they highlight different approaches, different technologies. First, IonQ. They're leaders in trapped ion quantum computing.
Trapped on, what's the key thing about that approach?
Well, trapped ion systems are known for being quite stable and having high-quality qubits. They're focused on building what are called gate-based quantum computers. Think of these as aiming to be general-purpose machines, like a future quantum CPU that could run many different kinds of quantum algorithms.
Okay, the universal quantum computer goal.
Kind of, yeah. And critically, IonQ isn't just research. They have systems available commercially, integrated into cloud platforms like Amazon Braket and Microsoft Azure Quantum. People are paying to use them.
Real revenue, real customers in areas like pharma and logistics.
Exactly. So they're building that general-purpose, cloud-accessible quantum future. Now compare that with D-Wave.
Right, D-Wave, different approach.
Very different. D-Wave uses a technology called quantum annealing. This isn't a universal gate-based machine. It's highly specialized. It's designed almost exclusively for one thing: solving large-scale optimization problems.
Finding the best solution among many possibilities, like scheduling or resource allocation.
Precisely. It's built to find the lowest energy state of a problem, which maps perfectly onto those kinds of optimization challenges: material science, logistics, financial modeling.
And this leads to that demo mentioned in the Bloomberg piece, the one that really highlights the speed difference.
Yes, that's the real aha moment, isn't
Got
it? Essential context. Their CEO, Alan Baratz, showed the D-Wave machine calculating properties of new materials. The task was completed in minutes.
Minutes. And the comparison, how long for a classical supercomputer?
That's the staggering part. The sources estimate that doing the same task classically would take the world's fastest supercomputer. Something like nearly 1,000,000 years.
1,000,000 years versus minutes.
I mean, think about that compression. A problem that's effectively impossible classically becomes solvable, well, instantly in quantum terms.
That's not just an advantage, that's a different reality. And it shows up on the balance sheet, right? D-Wave's growth.
Absolutely. They reported, what was it, nearly 400% year-over-year growth in gross profit in the first half of 2025. That's commercial validation. Their specialized optimization focus is clearly paying off.
So two distinct paths. IonQ with the general-purpose cloud model, D-Wave hyper-focused on optimization, both finding success.
Exactly. And of course, they're not alone. We should also mention folks like Rigetti Computing, Quantinuum. They're all part of this emerging ecosystem, building the infrastructure for what people are calling the quantum economy.
Okay, so we've covered the what, the how, the who. The big question for anyone listening is probably, why now? Why pay attention, maybe even invest in this now?
Well, the market forecasts are certainly one reason. Projections are showing the global quantum computing market hitting over $10 billion by 2030. That's hyper-growth territory.
Driven by what? Corporate R&D? Government funding?
Both. Plus, the pull from AI demanding more power, as we discussed. But beyond the numbers, it's the strategic positioning.
That seems critical. But are there risks? I mean, the hardware is still complex, expensive, not exactly plug and play yet.
Oh, absolutely. There are significant hurdles: infrastructure, accessibility, talent pipelines. These are real challenges. But the argument from the sources is that the demand from AI, especially for optimization and simulation, is so intense that it's forcing the issue. Companies feel they have to explore this to stay competitive. It's becoming less optional.
Which brings us back to that cloud analogy. Quantum as the next foundational layer. Get in before it's ubiquitous.
That's the parallel. Investing now is like getting into cloud before AWS scaled massively, or maybe more recently, like securing GPU capacity before the big AI boom hit. It's about positioning for the next computational shift.
So quantum is looking like the strategic frontier for the AI economy, redefining speed, but also sustainability and scale.
All three, yeah.
Yeah.
It seems to be the engine needed for AI to make its next really big leap in capability.
It's fascinating. We've really moved from does quantum even work to wow, look how fast it's changing the game. IonQ, D-Wave.
Yeah.
They're providing the proof. That million-year calculation becoming minutes.
That kind of speed up just changes the possibilities fundamentally.
So, if quantum plus AI can collapse calculation, times like that, from years down to minutes,
Yeah.
you have to wonder, right? What huge, previously unsolvable global challenge gets tackled first? Is it sustainable materials, personalized medicine, climate modeling? Which one falls first to this combined power?
That really is the multi-billion-dollar question, isn't it? And watching it unfold will be quite something.